Light doesn't just move fast, it sets the pace for reality itself. Push up against that limit and time slows, distances warp, particles refuse to die, and even black holes and the expanding universe obey the same number. In this video, we dig into Feynman's view of why light speed is the absolute cap on cause and effect, and what snaps if you try to beat it. You move through the universe at painfully low speeds, and most of the time you do not notice it. A typical passenger jet does about 900 kilometers per hour, around 560 miles per hour. The Earth going around the Sun does roughly 108,000 kilometers per hour, about 67,000 miles per hour. Those sound big, but now put them next to light in vacuum, about 300,000 kilometers every second, roughly 186,000 miles every second. In 1 second, light could wrap around Earth about 7.5 times. Your fastest machines do not even come close. Here's the first big point, and it is easy to miss. That speed, which physicists call c, is not just how fast light goes. It is so fundamental that we actually use it to connect the units of space and the units of time. 1 second of time multiplied by c becomes a distance about 300,000 kilometers. Modern physics treats c as a conversion factor between seconds and meters, between time and space. So when you hear the speed of light, you should not think only of flashlights and lasers. You should think, this is the number that tells the universe how to compare time and distance at the deepest level. That raises a simple question though. How did we even figure out this number from a small planet with crude tools long before satellites and atomic clocks existed? The story starts with astronomy. In the 1600s, Olli Roma watched Jupiter and its moon Io. Io goes behind Jupiter on a regular schedule like a clock. Roma noticed that sometimes those eclipses happened a bit earlier, sometimes a bit later, depending on where Earth was in its orbit. When Earth was farther from Jupiter, the events looked delayed. When Earth was closer, they looked early. He realized the only explanation was that light takes time to cross space, and the extra distance across Earth's orbit caused a measurable delay. His numbers were rough, but he proved light does not move infinitely fast. It has a finite speed. Later, on Earth itself, Albert Michelson pushed this much further. He set up a long path, several kilometers, and used rotating mirrors to bounce light out and back. By spinning the mirror fast and measuring how much it had turned between sending and receiving the light, he could estimate how long the light took for the round trip. From that, he could calculate the speed. His measurements kept getting better, and they closed in on the modern value of c. Today we change the game completely. We do not treat the speed of light as something we still measure every year. Instead, we lock it in by definition. In the metric system, the meter is defined as the distance light travels in a specific tiny fraction of a second. That means c, in meters per second, is exact, and we use it to define our ruler. When scientists say this is 1 meter, they are really saying, this is how far light goes in this much time. That is how central this number is. So far, this still sounds like just a very fast speed that we learned to measure very well. But Feynman kept telling students, do not think about c only as the speed of light. Why was he so insistent about that? If you take the equations that describe electric and magnetic fields in empty space and you ask how a disturbance moves through that empty space, the math gives you a wave. You can calculate the wave's speed from the constants that describe how strong electric and magnetic effects are in a vacuum. When you do that, you get exactly c, the same number as the speed of light in vacuum. This was known even before photons and quantum theory. It told physicists that light is literally an electromagnetic wave in the vacuum, and that its speed is not something optional. It falls straight out of the basic properties of empty space. Feynman's point was, even if you erased the word photon from your brain, and you only studied how fields behave in empty space, you would still discover this special speed. You would still find that disturbances in the electromagnetic field travel at c. That is why calling c just the speed of light is misleading. Light moves at c because it is one kind of disturbance in one field. but c itself belongs to the structure of spacetime and the fields that live in it. It is a built-in limit on how fast any influence can move if that influence is not stuck to a massive particle. Here is where things start to tighten. It would already be impressive if this special speed showed up only in electromagnetism, but it does not. When you write down the rules of special relativity, the rulebook that says how space and time transform when you move close to light speed, c appears as the one speed that looks the same to every observer. It defines what moving at the maximum possible speed means for everyone in every direction. Then you look at the famous relationship between mass and energy, the one that says energy equals mass times the square of the speed of light. The conversion between mass and energy uses c again. That same number tells you how much energy is locked inside a kilogram of matter, and how much energy you need to create that mass out of pure radiation. Nuclear reactors and stars run on that conversion. Go deeper into quantum field theory, the framework we use for particles and forces, and you still see c setting the limit for how fast signals can move. It shapes the light cones in spacetime diagrams, which separate events that can influence each other from events that can never be connected, no matter what you do. It appears in the formulas for how fields spread out, how particles propagate, how interactions fall off with distance and time. Over and over, different parts of physics point at the same number and say, this is the maximum allowed speed for any cause to produce any effect. So the real question is no longer how fast can rockets go or how fast can light go. The sharper question is, why does every serious law of physics treat this one speed as absolute, and what has to give way when you try to think about going faster? Because something does have to give, and the thing that breaks is not a rocket engine, it is your everyday idea of space and time. In other words, if c really is the conversion factor between seconds and meters, then maybe time is not an independent thing running alongside space. Maybe they are two faces of one structure, and c is the number that locks them together. Once you accept that, everything from time dilation to the speed limit starts to fall out of geometry, not technology. And that's exactly where we go next, when space and time stop being separate and c becomes the glue. Have you ever stopped and asked, what is 1 second actually made of in physical terms? Not on a clock, not in your head, but in the universe itself. If you take 1 second and multiply it by c, by those 300,000 kilometers per second, you get a distance, about 300,000 kilometers, around 186,000 miles. Physicists treat that as a real distance, not just a trick. In other words, 1 second of time is the same size as 300,000 kilometers of space, once you scale it by c. This is how physics quietly puts distance units onto time. In the equations, instead of writing time as a separate kind of thing, you multiply time by c and turn it into a distance. So instead of 3 coordinates for space and a different, weird coordinate for time, you get 4 coordinates, all in distance units. 3 are space and 1 is time multiplied by c. People call distances that light travels in some time light seconds or light meters. 1 light second is about 300,000 kilometers. 8 light minutes is roughly the distance from Earth to the Sun, about 150 million kilometers, around 93 million miles. This sounds very abstract, but there is a clear reason for it. If c is the built-in conversion rate between seconds and meters, then time does not sit in a separate category. It becomes another axis in the same arena as space. You normally live in 3 dimensions: left-right, forward-back, up-down. Physics insists there is a 4th, the direction you move when time passes, and c is what lets you measure that 4th direction in the same units as the other 3. Now comes the tension point. If time is just another kind of distance once you multiply it by c, and if you and someone else are moving differently, what exactly stays the same for both of you when you compare notes about what happened? There is a single quantity that refuses to change, no matter how fast you move, and it is called the space-time interval. Here is the idea in plain words. Take two events, for example, a flash of light from a star and your eye detecting it. Between those two events, some amount of time passes and some amount of distance is crossed. You and another observer moving at a different speed might disagree on the details. You might say, the star was this far away and the light took this long. The other person might say, no, it was a bit closer and the time was a bit different. Both of you can be correct from your own frames of reference. But when you combine the time difference times c and the space difference in a certain way, you get one space-time distance between those two events, and everybody gets the same value for that. That combined quantity is the space-time interval. You can think of it as the true separation in space-time, not just in space or just in time. Here is what that means for you. You're always moving through space-time. If you move faster through space, your motion through time has to adjust so that this space-time interval stays fixed. The universe treats your path the way it treats the length of a diagonal in a rectangle. If you stretch one side, the other side changes so that the diagonal stays the same. Except here, the C's are your motion through time and your motion through space. That is the deep geometric reason behind time dilation. When your speed through space gets close to c, your speed through time slows down relative to someone who stayed at rest. Your clock really ticks slower. Your heart really beats fewer times. Your aging rate drops. The space-time interval pushes everything to line up so that nobody can violate that fixed combined distance between events. But this is all still words. So the obvious next step is, what does this look like when you draw it? And how does c show up in the picture? Picture a simple graph in your mind. Time goes upward. Space goes sideways. One axis is distance in time, which is time multiplied by c, and the other axis is ordinary distance in, say, kilometers. On this graph, your entire life becomes a line, called your world line. Each point on that line is you, at some place and some time. Now look at what light does on this graph. Light moves 1 light second of distance in space for every 1 second of time. Since 1 second of time corresponds to 1 light second of distance in time, the path of a light beam is a line that goes up 1 unit and over 1 unit, over and over. That gives it a fixed angle on the diagram. No matter who draws the graph, light beams always sit at that same angle. That angle is literally the geometry of c. Feynman loved these space-time diagrams because they make cause and effect very clear. From any event, you can draw 2 lines at that light angle, one going up right and one going up left. Those lines form the edges of a cone shape when you include all directions in space. Everything inside that cone is what light or any slower signal could possibly reach in the future. That is your future light cone. Everything inside the cone coming up from below is what could have reached you from the past. Here is the strict rule. The world line of any physical object with mass must stay inside that cone. It can tilt a bit, meaning you move through space as time passes, but it can never tilt more horizontally than the light lines. If it did, that would mean you are covering more distance in space per unit of distance in time than light does, which means faster than c. The diagram simply does not allow that for real objects. So when we say nothing with mass can reach or exceed c, this is not just a statement about engines or fuel, it is a statement about the allowed slopes of lines in space-time. Tip a world line too far and you leave the allowed region. Feynman used this picture constantly to decide which processes in particle physics make sense and which do not. If a proposed process would require a line that crosses outside the light cone to transmit a real signal, it is out. The diagrams and the number c that sets their angles act as a filter for what is physically possible. That raises a tough question you cannot dodge. Are these diagrams just a neat way to draw things, or does the real world actually behave as if space-time is built this way? With c setting the cone and every clock and ruler obeying it? GPS gives you a very hard, very practical answer. GPS satellites orbit about 20,000 kilometers above Earth's surface, moving at over 14,000 kilometers per hour, around 8,700 miles per hour. Each satellite carries extremely precise atomic clocks. From your phone's point of view on the ground, those clocks are in two strange conditions at once. First, they are moving fast, so special relativity says their clocks should tick a bit slower than clocks on Earth. Second, they are higher up in Earth's gravity well, so general relativity says they will feel a weaker gravitational field, and their clocks should tick a bit faster. These two effects do not cancel. When you add them up, the net result is tens of microseconds of time difference every day between a satellite clock and a clock on the ground. A microsecond is a millionth of a second, and light travels about 300 meters, roughly 1,000 feet in that time. If engineers ignored these relativistic effects, the positions that GPS gives you would drift by kilometers each day. Your map would show you in the wrong street, the wrong district, eventually the wrong city. To prevent that, the whole GPS system is designed with relativity built in. The satellites are launched with their clocks deliberately offset, and the software continuously corrects for the difference predicted by Einstein's equations. This is not optional. If spacetime did not behave the way those diagrams and intervals say, GPS would fail. The fact that you can stand in the middle of a city, open your phone, and get a location accurate to a few meters is direct proof that the geometry of spacetime, with C gluing space and time together, is how the real world works. So now you have a universe where time is just another direction in a four-dimensional structure. C is the conversion rate between the time direction and the space directions, and every allowed path through that structure must respect the light cones. The next question is brutal and unavoidable. If that is the shape of reality, what happens when you actually try to chase a light beam and catch up to it? Can your common sense picture of adding speed survive in this geometry at all? How can a speed stay the same even when you chase it almost as fast as you possibly can? That is the core headache of relativity. Think about this setup. You're in a ship moving at 90% of light speed, 0.9 c, relative to Earth. Out in front of you there is a light beam. In everyday Newton-style thinking you would say, I'm going at 0.9 c, the light is going at 1.0 c, so relative to me it should look like it's only pulling away at 0.1 c. You subtract speeds. That is how cars work, that is how planes work, that is how your intuition is built. But every experiment that has ever checked this says no. If you measure the speed of light in vacuum, you always get the same value c, no matter how fast you're moving. You in the fast ship and somebody standing still on Earth both measure light in empty space at about 300,000 kilometers per second, roughly 186,000 miles per second. Not almost that, not that minus your own speed, but the same number. This is not a philosophy argument. This is what the data says, and it directly clashes with the simple rule new speed equals old speed minus my speed. So physics had a choice, either the experiments are wrong or your everyday idea of space and time is wrong, and the experiments did not blink. The key data that cornered everyone started with the Michelson-Morley experiment in the late 1800s. Physicists back then thought light might move through some invisible medium called the ether, the way sound moves through air. If that were true, Earth should sometimes be moving with the ether wind, sometimes against it, as it orbits the Sun. So the speed of light should look a little different in different directions and at different times of year. Michelson and Morley built an interferometer, a device that splits a beam of light into two paths at right angles, sends them down long arms, and then recombines them. If one beam had to fight against an ether wind, it would take slightly longer, and the recombined pattern of light and dark fringes would shift. They pushed their setup to insane precision for their time. They found nothing. The speed of light looked the same in every direction, within their sensitivity. No ether wind, no tiny change they could pick up. That null result was devastating for the ether idea. Over the years, people rebuilt and improved that style of experiment with better lasers, better mirrors, better vibration control, cavities, resonators, astrophysical observations. All of it kept pointing to the same thing. The two-way speed of light in vacuum is constant, independent of the motion of the source and independent of the motion of the observer, to ridiculous levels of precision. Once you take that seriously, your old picture of the universe cannot survive. That is exactly where Feynman's attitude kicks in, and it is brutally simple. The experiments do not care what you find intuitive. If the data and your mental model disagree, the model goes in the trash. To keep C the same for every observer, you must throw away the idea of absolute time and absolute space. Instead of one universal clock ticking the same in all places, each observer gets their own time. If you move fast relative to me, your clock really does tick slower than mine, as seen from my frame. Your rulers, along the direction of motion, really do contract, so you measure less distance between 2 points than I do. Two events that I say happened at the same time will, for you, be separated in time. That effect is called relativity of simultaneity. None of this is a choice. These weird effects are the only way to reconcile everyone measures the same C with the rest of physics. If you try to keep ordinary addition of speeds and keep one universal time, you instantly break the constancy of C. If you force C to be constant and keep your naive ideas about clocks and rulers, you break momentum and energy conservation. The only consistent fix is to let space and time bend, time dilation, length contraction, change simultaneity. Feynman's message was, accept the weird or you lose the experiments. Now, if speeds do not just add the simple way, what actually happens when you try to stack them? How does the universe block you from crossing C, even on paper? Relativity gives you a new rule for combining speeds. Do not worry about the full formula, just track the behavior. If you are moving at 99% of light speed relative to Earth, and you fire a probe forward that you say is going at 99% of light speed relative to you, someone back on Earth does not see that probe going at 198% of light speed. When you plug those numbers into the relativistic addition rule, the outside observer gets a speed of about 99.995% of C. So from your point of view, you gave the probe a huge extra push, but from Earth's point of view, it only crept a tiny bit closer to C. Another example, you cruise at 99% of C and fire something forward at half the speed of light relative to you. Newton style, you would expect 149% of C relative to Earth. The relativistic rule spits out something like 99.7% of C instead. The faster the base speed gets, the more the extra piece gets squeezed sideways into energy and time dilation instead of extra speed. There is a pattern. Anytime you combine two speeds that are both below C, the relativistic rule gives you a new speed that is still below C. You can push as hard as you like, you can chain as many boosts as you want. You can try insane accelerations in units of G for as long as your ship survives, but that ceiling is never crossed. For objects with mass, you can get closer and closer to C, but you will never hit it, and you will certainly never go beyond it. Light, which has no rest mass, always moves at exactly C in a vacuum, not slower and not faster. So when you think, I'll just keep accelerating and eventually I'll be doing twice the speed of light, the math disagrees. The extra energy you pour in does not translate into more ordinary speed. It goes into increasing your energy and momentum in a relativistic way, into cranking up the time dilation factor, into twisting your path in space-time, but it never gives you a world line that tilts outside the light cone. All of that still feels abstract until you ask the next question. If you can never catch the light beam, what does that do to your own time, to your own life, when you actually try to get close? How much can your clock really slow down? How far into Earth's future can you jump just by moving fast? That is where the theory slams into reality in a very direct way, with particles raining down from the sky, with protons in giant rings, and with the possibility that if you ride close enough to C, you and everyone who stayed home will end up living in completely different slices of time. How can something that should die in the sky reach you alive at sea level? That is the first sign that time at high speed does not behave the way you think it does. High energy cosmic rays hit the upper atmosphere all the time. You are getting bombarded every second. When they collide with air molecules, they create showers of new particles, including muons. These muons are born roughly 10 to 15 kilometers above your head, about 6 to 9 miles up. In the lab, when a muon is at rest, its average lifetime is only about 2 millionths of a second. Even if it could move at light speed, which it cannot because it has mass, that short lifetime would only let it travel under a kilometre, well under a mile, before it decays. But detectors at sea level see plenty of muons from those showers. By normal reasoning, they should not make it. On Earth, at rest, their internal clock says they die almost instantly. Yet many survive the full 10 to 15 kilometres down to ground level and trigger detectors. You can literally put a simple detector in a lab or a school and watch these things being counted. Something in your everyday picture of time and motion is wrong. From our point of view on the ground, the fix is clear. Those muons are moving at speeds extremely close to c. Because they're moving so fast, their internal clocks run slow compared with our clocks. The time between birth and decay for them is still about 2 millionths of a second in their own frame, but in our frame that interval is stretched. The slowdown factor is not random, it matches what special relativity predicts for objects moving that close to the speed of light. That extra lifetime, as measured on Earth, is enough for them to cross those 10 or more kilometres before they vanish. You can flip the viewpoint and the story is just as weird. In the muon's own frame, its clock is normal, and it still only lives those tiny microseconds. What changes instead is the thickness of the atmosphere. Because of length contraction, the distance from where the muon is created to the ground is squeezed. The muon sees only a much thinner layer to cross, so it has enough time to reach the surface before decaying. Two different stories, same geometry, same data. Either way, the conclusion is the same. When you get close to c, you're not just changing speed, you're warping how time and distance work for you. So if nature is stretching time for particles falling through the sky without asking your permission, what happens when humans deliberately push particles to even higher speeds and trap them in a ring? In particle accelerators like the Large Hadron Collider near Geneva, protons run around a circular tunnel about 27 kilometers long, roughly 17 miles. Magnets force them to curve and keep them on track, while radio frequency cavities kick them again and again, ramping their energy up. At full power, those protons move at more than 99.999999% of light speed. The difference between their speed and c is just a few meters per second, like a slow jog compared to 300,000 kilometers per second. Inside those beams, unstable particles are constantly being created and destroyed. Take one of those particle types, measure its lifetime at rest in the lab. Then look at the same kind of particle inside the beam, flying around the ring at almost c. Its lifetime is now many times longer. It lives far beyond what the at-rest number says it should. You do not get a small tweak, you get a huge extension. When physicists crunch the numbers, the stretching of the lifetime lines up with the relativistic time dilation factor that depends on how close you are to c. The closer the beam energy gets to that limit, the more extreme the factor becomes. Time along the particle's path really does slow down relative to the lab's clocks. For some particles, the lifetime in the accelerator can be hundreds of times longer than at rest. If you try to analyse these beams using ordinary non-relativistic formulas, your predictions would be completely wrong. Particle physics would just not match experiment. This is humans using technology to twist the flow of time for particles on demand. Turn up the energy, you turn up the time dilation. Turn it down, everything returns to normal. The same space-time rules that save the muons from dying in the upper atmosphere show up inside these machines, under our control, and they behave exactly the same way. Next step, scale this up from particles to you. What happens to your own life if you get close enough to see and stay there for a while? If you could ride in a ship that cruises at 99% of light speed, and you travel for 5 years according to the clock on board, you experience only those 5 years. You eat, you sleep, you age those 5 years. But when you come back to Earth, you do not find that 5 years have passed here. You find that far more time has gone by back home, maybe decades, depending on your exact speed and route. From your point of view in the ship, your time feels normal. You do not feel slowed down. Your heart still beats at a normal rate, you still get 1 second per second. It is only when you put your clock next to a clock that stayed on Earth that the gap hits you. The Earth clock has ticked through many more days and years than you have. Friends and family are older, maybe gone. You have effectively jumped into Earth's future by moving fast and then coming back. This is the twin paradox in plain language. One twin stays on Earth. The other twin goes on a high-speed round trip near sea and returns. The travelling twin has aged less. There is no real paradox once you draw the space-time diagram. The two twins follow different paths through space-time with different accelerations and different world lines. The space-time interval along the travelling twins' path is smaller, so less proper time elapses for them. It is the same geometry you saw with muons and accelerator particles, now applied to human lifetimes. The universe is absolutely consistent, just not kind to your intuition. And this is not science fiction parked in some unreachable future. We already see small versions of this effect with real hardware. Astronauts on the International Space Station experience a mix of special and general relativity, very similar in principle to the corrections we have to do for GPS satellites. Atomic clocks flown on aircraft and compared to clocks left on the ground show measurable shifts right where special relativity says they should be. The shifts are tiny at airplane speeds, but the numbers match the same time dilation factor the muons and the LHC obey. That is why Feynman liked these timing experiments so much. They are not arguments on a blackboard. They are stopwatches, counters, detectors, and flight paths. Cosmic Raymian counts, unstable particles in rings, clocks in orbit, clocks on planes, GPS satellites that must be corrected every day or your maps fail. They all tell one story. When speed gets close to c, time dilates according to one clean factor, and that factor is built around the same constant c that controls light and causality. Relativity is in the stopwatch, not just in textbooks. So the speed limit is not just sitting out there as a rule about velocity. It is wired into how fast things can age, how long particles can exist, how much you can bend your personal timeline by moving fast. Every precise clock pushed hard enough starts to reveal that there is a wall you cannot cross by speed alone. And that sets up the next hard question. If time itself is bending to protect this limit as you go faster, what happens is when you try to brute force your way to c with raw energy? How big is the energy bill if you want your ship or even a single proton to almost touch that limit? And why does the universe make that bill explode just before you get there? Why does throwing more and more energy at something stop giving you more speed and start giving you something much stranger instead? In school, you learn a simple rule for kinetic energy. Take the mass, multiply by the square of the speed, divide by 2. In that picture, if you keep feeding energy into an object, the speed just keeps climbing. Double the energy, push the speed higher, do it again, higher again. There is no built-in limit. That rule works well for cars, planes, bullets, even rockets, as long as their speeds are small compared to light. Relativity rips that up when you get close to c. The deeper rule says the total energy of something with mass is its rest. Mass multiplied by the square of the speed of light, multiplied again by that same time-stretching factor we talked about before, the factor that tells you how much your clock slows down near light speed. At low speeds, that factor is almost 1, so you can peel off a little piece of the total energy, and it behaves like you're familiar, half mass times speed squared. That is why Newton's formula works so well for everyday life. But as your speed creeps towards c, that time-stretching factor does not stay close to 1. It starts to climb, then skyrocket. Every extra chunk of energy you pour in mainly goes into making that factor bigger, not into pushing the speed much higher. You're not so much making the object move faster through space, you're changing how steeply it cuts through space-time, and you pay more and more of your energy bill into that angle instead of into extra kilometers per second. So here is the sharp question. If this is really how nature charges you for speed, can we see that bill being paid anywhere? In hard numbers, not just in theory. Look at what we do to protons in the Large Hadron Collider. They run around a ring 27 kilometers long at energies of several trillion electron volts per particle. That energy is so huge, measured per proton, that their effective mass, from the lab's point of view, is thousands of times larger than their rest mass. It is like taking a tiny grain of sand and giving it the inertia of a brick, then a boulder, then a truck, as you crank the energy higher. The magnets and radio systems are still pouring power into those beams, turn after turn. But if you calculate the actual speed, it is already so close to c that you can barely see the difference. You're talking about a shortfall of just a few meters per second from 300,000 kilometers per second. In miles, that is a gap of maybe a dozen miles per hour out of 670 million miles per hour. You spend an enormous amount of energy, and all you buy is a speed increase so small it is hard to even describe in normal terms. That is what the energy wall looks like in the lab. The more energy you add, the more that relativistic factor swells, the more the particle's relativistic mass shoots up, and the less extra speed you get for your money. You're spending a fortune to shave microscopic fractions off a finish line you're never allowed to touch. And that is just for a single proton, a subatomic speck. So what happens when you scale this to something you actually care about, like a starship with people on board? Take a ship with a mass of 1 million kilograms, about the mass of a decent-sized ocean liner, or a big skyscraper chunk of metal and machinery. To push that whole thing to 90% of light speed, you are now talking about an energy requirement on the order of months or years of total human energy production at today's levels. All the electricity, all the fuel burned, all the reactors running, all focused into one vehicle. And that only gets you to 0.9 C. Now try to push from 90% to 99% of light speed. The relativistic factor jumps sharply. The extra energy needed for that last 9% is not small top-up. It is more than you spent getting to 90% in the first place. Go from 99 to 99.9%, the bill explodes again, far beyond anything a planet-scale civilization could realistically generate and throw away on one ship. And remember, this is only the ship's kinetic energy. In any real propulsion system, you also have to accelerate fuel, dump waste heat, and survive the forces on the structure. If you try to maintain a high constant acceleration, even a comfortable 1g, for years, the power and engineering problems stack up in ways that make current rocket science look like toys. The key point is this: as your target speed approaches c, the energy required per tiny extra decimal place in your speed grows without limit. Mathematically, it tends toward infinity. There is no just push harder path that gets you through c. You hit an energy wall that is not just very high, it is fundamentally uncrossable. No realistic fuel, no advanced reactor, not even turning a planet into propellant lets you actually break that limit for a ship with mass. So where does Feynman fit into this picture of walls and limits? He kept pointing back to the same relationship. When people quote the famous line about energy and mass, they are saying that any mass sitting in front of you is actually a huge reservoir of stored energy, and the conversion rate between mass and energy is the square of the speed of light. Take 1 kilogram multiplied by c squared, and you get a number so large it explains why nuclear reactions are so powerful even when only a tiny fraction of the mass converts. That same conversion rate, c squared, is sitting inside the relativistic energy expression that blows up as you approach light speed. It is in the rest energy, in the kinetic energy, in the way mass and energy trade off in particle reactions, in the way photons carry momentum even though they have no rest mass. It is the same c that sets the maximum speed, the same c that glues space to time, the same c that fixes the slope of light cones. Feynman's consolidation is simple and sharp. Mass is energy, c is the conversion factor, and the geometry of space-time clamps how fast that energy can move information or influence around. The speed limit, the energy wall that stops your rockets, and the power of nuclear reactions are not three separate stories. They're all different faces of one rule, written with the same constant. If you want a universe where energy and mass can turn into each other, where cause comes before effect and where clocks and rulers behave consistently, c has to sit there as the master number enforcing the limit. So if brute force with energy cannot smash the speed limit, maybe the way out is not to push harder, but to think differently. Quantum mechanics says particles do not even take single paths, They explore every path at once in some sense. That sounds like a cheat code. If light can try all possible routes between 2 points, is there any way for that quantum weirdness to sneak around C and outrun the classical picture? How can light act like it is everywhere at once, but still never beat the speed limit that holds the universe together? That is the puzzle Feynman attacked head-on. In normal thinking, a photon going from point A to point B should follow a single path, a straight line in empty space or a bent line through a lens. In Feynman's quantum view, that picture is too simple. The rule is the photon does not commit to one path. It tries every possible path between A and B, every zigzag, every loop, every ridiculous detour. For each path, the theory assigns a number called an amplitude. You can think of it as a little complex tag that carries both a size and a phase, but you do not need the detailed math, only the logic. To find the chance that the photon actually shows up at B, you do not pick one path. You add the amplitudes from all paths, and then only after that do you square the result to get an actual probability. This is the core of the path integral idea. Nature does not roll dice on one trajectory, it sums over a whole swarm of them and lets the interference between them decide what you will see. Now the crucial pattern, paths that are wildly different from each other usually cancel out. Their amplitudes come with phases that do not line up, so when you add them, they mostly wipe each other away. Paths that are close to each other and close to the path that would give you the least action in classical physics add up instead of cancelling. They reinforce each other. The net effect is that out of this insane sum over all paths, the final probability is dominated by paths similar to the classical one, and the rest fade into the background. This sounds abstract, so connect it to something you already know. You learn in optics that light seems to choose the path that takes the least time between 2 points. This is Fermat's principle. Light bends when it enters glass or water, so that its travel time is minimized, like it is choosing the fastest route. In classical physics, that is just a rule. You accept it and move on. In Feynman's picture, you do not need light to be smart or to optimize anything. The path integral does the selection automatically. Every possible route through the glass is tried in the calculation. But paths that differ a lot in travel time end up with amplitudes that are badly out of phase with each other. When you sum them, they cancel. Paths that are close in travel time have similar phases, so their amplitudes strengthen each other. The surviving contributions cluster around the path where small changes do not change the total travel time much, which is usually the least time path. So when you see a laser beam refract through a block of glass, it looks like light is acting with purpose, taking the quickest route allowed by the slower speed in the material. Underneath what is really happening in the math is a giant interference pattern of all possible paths, with only the ones near the classical route surviving the quantum bookkeeping. But if photons are exploring all paths in this abstract sense, you might be tempted to ask a dangerous question. Could there be paths that sneak information around the light cone? Paths that make an effect outside the allowed causal region? And do we get faster than light influence from that? The answer from quantum field theory is no, and C is the reason. The amplitudes assigned to paths are not arbitrary. They are built from the space-time structure that already has C wired in as the maximum signal speed. When you work out how a photon's amplitude depends on the separation between A and B, the dependence is such that contributions that would correspond to a cause affecting something outside its light cone either cancel out or never add up to a measurable signal. Put it in simpler terms. You can write down a mathematical object that tells you the amplitude for a particle to go from one space-time point to another. That object falls off and oscillates in a way that respects the light cone. Points that are separated in a way that would require faster than light travel are not connected by a usable, controllable influence. The theory allows virtual processes and weird intermediate steps inside the math, but when you calculate actual detection probabilities, you never get a net effect that carries information outside the limit set by C. Feynman diagrams, those little sketches with lines and vertices, are just a compact way to organize these path integrals. Each internal line in a diagram corresponds to one of these propagators, one of these amplitude rules for going from one point to another. Each external line hooks up to real particles you can prepare and detect. The rules for the lines and the vertices are tuned so that when you add up all the diagrams that contribute to a process, you get results that respect causality and the speed limit. You do not have to put that in by hand every time. It is built into the structure of the theory. This is where things get really tight. Quantum electrodynamics, the theory that uses Feynman's path integrals and diagrams to describe electrons and photons, has been tested to absurd precision. People have calculated the magnetic moment of the electron using QED and compared it to experiments that measure that magnetic property. The agreement goes out to many decimal places. Scattering experiments, where electrons and photons smash into each other at high energies, match the cross-sections predicted by the same theory. Tiny shifts in atomic energy levels, like the Lamb shift in hydrogen, are nailed by QED calculations. In all these cases, the path integral machinery is running in the background. The theory is summing over paths, letting amplitudes interfere, and using propagators that respect the light cone structure set by C. If there were any way for that machinery to leak a real, controllable signal outside the light cone, if there were any hidden path that gave you a usable faster-than-light channel, these ultra-precise tests would be the place where the cracks show. They do not. You can set up double-slit experiments, you can play with beam splitters, you can run photons through kilometers of optical fiber, you can create entangled pairs and send them to opposite sides of a lab or even to different buildings. The interference patterns and correlation statistics you see match quantum predictions built on Feynman's rules. But there is no configuration where you can flip a switch at A and have a message show up at B outside B's light cone. You always need a normal, slower-than-light channel at some point to compare results and see the weirdness. That is the core message here. Quantum mechanics does not rescue you from the speed limit. It makes the story stranger, it replaces single trajectories with sums over all paths, it introduces amplitudes and interference instead of simple probabilities, but it does not let you outrun C. In fact, the more you lean into the full quantum field theory, the more you see that the constant C is buried in every piece of the math that tells you how fields propagate and how particles interact. So even the crazy trick where light takes every path is still playing inside the same cage, the cage defined by the light cone and the invariant speed. And that brings you to another apparent loophole people love to push. If light can slow down in glass or water, and if particles can move through that material faster than light moves there, does that mean you found a way to beat the limit? Or is that yet another illusion that collapses when you look at what C really means? How can something move faster than light and still not break the rule that nothing outruns C? This is where the wording starts to trick you. Start with a simple fact. In empty space, light moves at C, about 300,000 kilometers per second, about 186,000 miles per second. That is the clean fundamental value. But real life is full of stuff: air, water, glass, fiber optic cables. When light goes through a material, it effectively slows down. In water, the effective speed is roughly 3/4 of C. In typical glass, it is closer to 2/3 of C. What is going on there is not that the photon gets tired. It is that the electromagnetic wave is constantly being disturbed by the atoms in the material. The light field makes electrons in the atoms wiggle, the atoms re-radiate light, those re-radiated waves interfere with the incoming wave, and the net effect is a delay in how the pulse moves forward. You can track this with a refractive index, a number that tells you how much slower light goes compared with vacuum. That slowdown is exactly why lenses work. When light enters glass at an angle, it changes speed, and that change in speed bends its path. That bending lets you focus light in a camera lens, in your eye, or in a giant telescope. In fiber optic cables, the refractive index profile keeps light bouncing along the core, trapped by total internal reflection, so you can send data over hundreds or thousands of kilometers with very little loss. So yes, in a material, the effective light speed is lower than C, but the real fundamental limit still lives in the vacuum, and that is the one that shows up in relativity and causality. And that sets up the next confusing question: if light slows down in a material, Can a particle outrun it there and create something that looks like a visual boom? That is exactly what Cherenkov radiation is, and it is not a loophole, it is confirmation of how the rules apply. In nuclear reactors and big particle detectors, you often see a blue glow in water or other transparent media. That glow is Cherenkov radiation. It happens when a charged particle, usually an electron, moves through a medium faster than light moves in that medium. Remember, faster than light in the medium, not faster than C in vacuum. The particle carrying electric charge disturbs the electromagnetic field in the material. If it moves slower than the local light speed, those disturbances spread out smoothly as ordinary radiation. If it moves faster than the local light speed, it outruns its own disturbance, and the waves pile up in a cone, a shock wave of light. It is directly analogous to a sonic boom. When a jet moves faster than sound in air, it outruns the sound waves it creates, and those waves line up into a shock front, which you hear as a boom. Cherenkov radiation is the electromagnetic version. The blue light is the visible part of that shockwave, but the key detail is non-negotiable. The particle is still moving slower than C in vacuum. It is only beating the reduced effective light speed inside the material. The underlying causal speed limit is untouched. Nothing in that setup lets you send a signal faster than C in empty space. Next, people try a different trick. They make patterns move faster than light and then quietly call the pattern a thing. That is where laser spots and shadows come in. You can take a laser pointer and sweep the beam across a distant wall. If the wall is far enough away, the bright dot can move across the surface faster than C just by pivoting the pointer quickly. Scale it up, sweep a laser across the moon. The spot can race across the lunar surface at an apparent speed greater than 300,000 km per second. But the spot is not an object travelling along the wall. It is a sequence of different photons, each one going straight from your laser to a different point. No single photon is racing sideways along the surface. Each photon still travels through space at C in vacuum, hits one location and stops. The moving dot is just where the beam happens to hit at each moment. The same with a shadow. If you wave an object in front of a distant light source, the edge of the shadow can sweep across the surface faster than C. But there is no material or signal moving along that edge. It is just the boundary where light happens to be blocked at any given moment. It is like the moving intersection point where two scissors blades close, which can move quickly across the blades without any piece of metal travelling that fast. The crucial point is this: you cannot use these superfast patterns to send a controlled message from A to B faster than C. You cannot flip the laser on in a way that forces a superluminal pattern to deliver information to some specific point before any normal light or radio signal could get there. The pattern speed is not a signal speed. And this is the general pattern behind most faster-than-light claims you see pop up in headlines or popular articles. Sometimes people talk about effective speeds in materials, where you can define group velocities, phase velocities, all kinds of technical speeds that describe how certain wave properties move. Some of those can be made to go faster than C on paper, or even negative, by clever tricks with pulses and materials. But when you look at the part of the pulse that actually carries new information, the front edge, that front still travels at or below C. No usable message gets out ahead of the light cone. Sometimes the claim is based on pattern speeds, like the moving laser spot or the sweeping shadow, where nothing physical travels along the path at that advertised speed. Sometimes it is a statistical or interpretational trick, where average positions or changes in a wave packet are moving in a way that looks superluminal. But any attempt to encode and decode a real signal reveals that you are still limited by C. So when you see faster than light in news headlines, the first questions to ask are simple. Is this talking about light in a medium where the vacuum limit still applies underneath? Is this just a pattern speed? Is this some kind of pulse reshaping where the signal front is not actually outrunning C? In almost every serious case, once you dig into the details, the answer is yes. It is one of those tricks. The question that matters is always the same. Can you send a usable message, a controllable influence from A to B, so that B gets it before any signal limited by C could arrive? Every experiment that tries to push that boundary whether with exotic media, weird wave packets, or advanced detectors, keeps running into the same hard stop. When you insist on a real signal, not a pattern illusion, not a redefinition of speed, the answer is still no, and this is where the stakes jump. If you could really send signals faster than C, relativity would let you turn that into signals that go backward in time in some frames, and then you would be staring straight at logical paradoxes, warnings from the future, and kill your own past scenarios. The next step is to look at how C does more than limit speed. It actually protects cause and effect from tearing themselves apart. How do you break the universe with a single signal, and why does C stop you from doing it? Start with the nastiest thought experiment. Say you somehow build a machine that sends a signal faster than light, maybe 10 times C, maybe 1,000, it does not matter, just instant enough for your taste. You sit on Earth, your friend is on a spaceship far away, and you zap a message that reaches them before any light signal could get there. In your frame, the message clearly goes forward in time, because first affects second. Now switch to another observer, moving at a high speed relative to you. Relativity says there is no single true time order for events that are separated mostly in space. The order can flip between frames. If your signal is fast enough, there will be some frame where the reception happens before the sending. In that frame, your friend gets the message, reacts, and sends a reply back, also faster than light, in a way that, in your original frame, arrives before you send the first signal. With enough for clever setup, you can create a loop. You send a warning, do not press the button. Your past self gets the warning in time, does not press the button, which means the warning is never sent. You have a message that prevents itself from existing. That is the core of the grandfather paradox. Cause and effect break down. The logic chain loops and clashes with itself. This is not just a story, it drops straight out of the equations if you allow faster than light signals. The math of relativity lets you build a closed causal curve as soon as you give yourself the tool of superluminal messaging. That is why people take the speed limit so seriously, break it, and you're not just going fast, you're ripping the basic order of events apart. So the real question is, how does the universe stop this from happening in practice? What is the actual structure that keeps cause and effect in line? Go back to the space-time diagram you built earlier. Time is the vertical axis, space is the horizontal axis. From any event, any specific point in space-time, you can draw two lines that represent light rays going out in opposite directions, one up right, one up left. If you spin this picture in your head to include all directions in space, those two lines become the edges of a cone. Everything inside the upper cone is your future light cone. Those are all the events that can possibly be affected by what happens at your starting point, using any signal that does not exceed C. Everything inside the lower cone is your past light cone. All the events that could, in principle, have influenced you with signals at or below C. Then there is the region outside both cones. Those are events that are too far away in space and too close in time for a light speed or slower signal to connect you. No matter what you do, you cannot send a message from your event to one of those space-like separated events without outrunning light. You also cannot possibly have been influenced by them yet. That cone-shaped structure acts like a fence. It tells you what can causally talk to what, and C fixes the angle of that fence. In this language, the statement "nothing can send a signal faster than C" becomes "no real influence can jump outside the light cone." That is why the speed limit is really a geometry rule. It is not just about vehicles, it is about which pairs of events can be linked by any physical cause and effect chain. You might ask, is this just a nice picture? Or do we see this light cone structure in real, violent events out in the universe? Look at neutron star mergers, the collisions of ultra-dense dead stars. When two neutron stars spiral into each other and merge, they release energy in two ways that we can detect: gravitational waves, ripples in space-time itself, and electromagnetic radiation, light and gamma rays. LIGO and similar detectors pick up the gravitational waves, telescopes pick up the light. When we measured the arrival times from a famous event like this, the difference between the gravitational wave signal and the gamma ray burst was on the order of a couple of seconds, after both had travelled over hundreds of millions of light years. Over that distance, a difference of a couple of seconds means the speeds are matched to an insane precision. Basically, both are travelling at c within the margin of error. There is no sign of gravity barking orders ahead of light, no sign of some hidden influence racing outside the light cone. In particle collisions at accelerators, when two beams smash together, you can map the directions and timing of the sprays of particles. The correlations between them fit a picture where the underlying influences propagate at or below c. In gamma ray bursts, in supernovae, in flares from black holes, the timing of different signals lines up with what you get from a universe that respects the light cone boundaries. If there was some common, obvious effect that jumped ahead of c, these high-energy astrophysical labs would be where you find it. They don't. That brings you to the last suspect, quantum field theory, where everything already looks bizarre. You have virtual particles, vacuum fluctuations, fields everywhere, sums over histories. If there was going to be a secret backdoor for causality, it would probably hide there. Does it? Here is where the technical structure becomes your shield. In quantum field theory, the basic objects you use to describe measurements and interactions, these operators, are built with a strict rule. If two of them are associated with points that are space-like separated, meaning outside each other's light cones, then in the theory they effectively do not disturb each other in a way that can transmit a signal. More precisely, their order does not matter. They commute, so no experimenter can use one to send a controllable message to the other. Feynman diagrams may look like particles jumping around arbitrarily, with lines connecting distant points and virtual particles doing weird things behind the scenes. But those diagrams are just a way to organize a calculation. When you actually compute observable quantities, like cross-sections and decay rates, the contributions from processes that would break the light cone structure either cancel or never show up in the measurable outcomes. Even when you have internal lines in a diagram that mathematically connect space-like points, those lines represent virtual off-shell processes, not real signal-carrying particles. The rules of the theory make sure that nothing you can actually control in a lab lets you turn those into faster-than-light messages. The causal order defined by c and the light cones is baked into the algebra. Feynman's view of this was very practical. You can allow all kinds of weird intermediate steps in the math as long as, at the end of the calculation, no observer can exploit them to violate causality. The moment you could actually set up an experiment where a knob turned in one place forces a result outside its future light cone, the theory would be dead. Quantum field theory survives and thrives precisely because it passes that test over and over. So c is not only a speed limit, it is the constant that shapes the light cones, and those cones are the walls that protect cause and effect from tearing themselves apart. Break that, and you break logic itself. Now here is the jump in tension. Quantum physics also gives you entanglement, where two particles seem to know about each other instantly over long distances. Einstein called it spooky action at a distance. Sounds like the exact things he's supposed to forbid. So the next question is sharp. Does entanglement crack the light cone and sneak information through? Or does the universe somehow keep the weirdness and the speed limit at the same time? How can two particles act linked across huge distances and still not be a secret faster-than-light phone line? Einstein and two colleagues Podolsky and Rosen set up the shock. They imagined a pair of particles prepared in one shared quantum state then sent far apart. The details do not matter right now. Think of some property like spin, a kind of built-in yes/no answer. Quantum mechanics says the pair is in a combined state where neither particle has a definite value on its own, but together they are locked. If one is up, the other is down, and vice versa. You measure particle A here, you get up. Instantly you know particle B, light years away, will give you down if measured the same way. If you got their down here, you'd know B must be up. That looks like instant communication. You choose what to measure here, you see a result here, and somehow immediately the other side knows how to line up with that choice. Einstein hated that. He called it spooky action at a distance. His instinct was that quantum mechanics had to be incomplete, that the particles must carry some hidden internal instructions from the start, telling them how to answer any possible question without needing to talk faster than light later. That was the EPR argument. Either quantum mechanics is not the full story, or locality, the idea that nothing jumps outside the light cone, is dead. For a long time, this was just a philosophical fight. Then John Bell turned it into something you can attack with an experiment. Bell took the EPR setup and asked a simple, sharp question. If the particles really just carry hidden instructions with them, and no faster-than-light influence is allowed, what is the maximum strength of correlation you can ever see between their answers? He wrote down an inequality, a numerical limit, that any such local hidden variable theory must obey. If experiments break that limit, the local classical picture is out. Modern Bell tests do exactly this. Experimentalists create entangled pairs of photons or ions, send them to two stations separated by kilometers, sometimes tens of kilometers. Each station has a detector that can choose at the last moment which property to measure, for example, which polarization angle to test. The choices are made by fast electronics or even by random number generators. The two sides are shielded so that no ordinary signal at or below C can get from one station to the other in time to coordinate the results. They run huge numbers of trials and collect statistics. The result, over and over, is that the correlations between the two sides are stronger than any local hidden variable model allows, and they match the predictions of quantum mechanics. There is no way to explain the data by saying each photon carried a pre-written list of answers and just revealed it. The universe really does behave in this non-classical, entangled way. So it is tempting to say, fine, the particles are clearly talking instantly, so why not use this as a faster-than-light channel? Here is the crucial block. You do not control the individual outcomes. At each station, the measurement results look random. You get up, down, up, down, with probabilities given by quantum rules. The other side also sees a random sequence. The only non-random thing is the correlation between the two sequences when you compare them afterward. If you and a friend each sit by an entangled detector and just watch your local readout, you cannot tell from your side alone whether the other person is even there, what basis they chose, or what pattern they got. Your data stream looks like noise. Only later, when you bring the two logs together using a normal, slower-than-light channel, do you see the quantum pattern. Whenever you both measured in matching ways, your results are linked in the stronger-than-classical way that Bell's inequality talks about. Because you cannot choose to force your detector to spit out up or down on demand, you cannot encode a bit of information in the entangled outcome. You cannot say, I'll send a 1 by making my side always read up. Quantum mechanics just does not let you do that. Your choice of what to measure can change which correlation pattern shows up when the data are compared, but it cannot force a specific outcome at the other end that they can read in isolation. So entanglement gives you spooky correlations, but not a controllable superluminal telegraph. You can't send a usable message from A to B faster than light with it. The universe gives you weirdness, not a cheat code for causality. Feynman's stance on this was very down to earth. In the language of quantum field theory, the operations that correspond to measurements at two spacetime points are built so that, when those points are outside each other's light cones, the order of those operations does not matter. Technically, the operators commute. Practically, that means whatever you do here cannot be used to influence the statistics there in a way that can be detected without bringing the data together inside a light cones. Even with the entanglement, even with virtual particles, even with all the internal complexity of Feynman diagrams, the final observable quantities respect the same rule. No experimenter can set up a protocol that sends a classical message outside the causal structure defined by C. The math is written to keep that no signaling condition locked in, so you end up with a strange balance. Entanglement tells you the universe is more deeply connected than any classical picture allows. Bell tests say hidden, local instructions are not enough, and yet the speed limit and the light cones still stand. You get non-local correlations, but you do not get non-local communication. Feynman's approach is to accept that, calculate within it, and let the experiments be the final judge, they keep saying the same thing. Quantum mechanics is weird, but it is not your ticket to outrun C. That leaves one more huge apparent violation sitting out there though. On the largest scales we can see galaxies are receding from us so fast that many of them appear to be moving away faster than the speed of light. The light from the most distant regions of the universe is redshifted so strongly it screams extreme motion. So the next question hits hard. If nothing can move through space faster than C, how can entire galaxies and even the fabric of space between them seem to blow past that limit? How can whole galaxies seem to race away faster than light, while the universe still refuses to let anything actually outrun C? Hubble's key observation was simple in concept, brutal in consequence. Take many galaxies, measure how bright they are to estimate their distance, then look at their spectra, the fingerprints of the elements in their stars. Those fingerprints are shifted toward the red end of the spectrum, and the farther the galaxy is, the bigger the redshift. Interpreted as motion, that redshift means the galaxy is receding and the speed is roughly Hubble's constant multiplied by the distance, so double the distance, double the recession speed, triple the distance, triple the speed. Now extend that line. At some huge distance, the recession speed you get from this speed equals constant times distance rule passes C. Go far enough and you are talking about galaxies whose recession speed in this sense is 2 times C, 10 times C, more. If you treat those numbers like normal velocities, the universe looks like it is casually breaking its own speed limit on the larger scales. The trick is that this speed is not ordinary motion through space. In general relativity, the geometry of spacetime is not rigid. Distances are defined by a metric, a rule that tells you how far apart 2 points are. That metric can change with time. When cosmologists say the universe is expanding, what they mean is that the scale factor in that metric is growing. The ruler built into space is stretching. Picture 2 galaxies sitting still with respect to their local space. They are not firing rockets, they are not ploughing through some cosmic air. But as the scale factor grows, the distance you assign between them increases. New space is appearing in between. If they start 1 billion light years apart and the scale doubles, they become 2 billion light years apart, even though neither galaxy felt a local wind or acceleration. On small scales, like inside a galaxy or a solar system, gravity and other forces dominate and hold things together, so you do not see this stretch. Your meter sticks do not grow, your body does not expand with the universe. But over tens, hundreds, and billion ends of light years, the expansion shows up as this Hubble recession. That is why cosmologists are comfortable talking about recession speeds bigger than C without panicking. No galaxy is locally punching through its neighborhood faster than light. In any small enough region of space around any observer, physics looks like special relativity, and C is the same old limit. It is the global bookkeeping of distances between faraway galaxies that gives you those supersized numbers. The obvious test is, does this stretchy metric picture actually match what we see when we look deep into space, not just at individual galaxies, but at the leftover glow from the early universe itself? The cosmic microwave background is that glow. It is radiation released when the universe was about 380,000 years old. When it cooled enough for electrons and protons to combine into neutral atoms and let light travel freely. Today that light is stretched into microwaves with a temperature of about 2.7 degrees above absolute zero. It fills the sky in every direction. When you map tiny temperature variations in the cosmic microwave background, you get a pattern of hot and cold spots with specific sizes and correlations. Those patterns encode how the universe expanded and how matter clumped in the early stages. The data tell you that regions of space that are now vastly separated, tens of billions of light years apart, were once close enough to exchange light and influence each other. The early universe was much smaller and denser. Light cones overlapped. Signals could cross between regions. To get from that connected early state to today's stretched out universe, you need the scale factor to grow by an enormous factor. There is strong evidence that in the very early universe, There were periods where this expansion was extremely rapid, much faster than the steady Hubble expansion you see today. People call that inflation. During those periods, distances between far points grew so fast that recession speeds between them easily blew past c. But again, what is growing is the metric, not objects tearing through a fixed background. Locally during inflation or now, no particle with mass ever has a world line that tilts outside its light cone. No observer sees a neighbour rocket past at more than c. The rules of local causality do not get suspended just because the global scale factor is changing quickly. This is exactly the kind of thing Feynman liked to cut through with one sharp reminder. Speeds are not absolute. They depend on how you choose your coordinates. In cosmology, you usually pick coordinates where galaxies, on average, sit at fixed positions, and the scale factor in front of the spatial part of the metric grows with time. In that picture, space expands and galaxies ride along, and recession speeds can exceed c. You can choose a different coordinate system where space is fixed and distant galaxies are assigned huge peculiar velocities instead. The math rewrites itself. Distances and times get relabeled. But the real physical question is not, what number do I write down for the recession speed? It is, can any actual observer anywhere send or receive a signal faster than c in their local frame? Every serious observational test says no. The cosmic microwave background pattern fits more with certain models where information and light were limited by c in the early universe. Large-scale galaxy servers mapping how galaxies cluster over hundreds of millions of light-years line up with the same expansion history. Neutron star mergers show gravity and light moving at essentially the same speed over cosmological distances. None of this looks like a universe where some hidden mode of influence is racing ahead of a light to stitch distant regions together. So even when you talk about galaxies faster than light, what you are really seeing is a coordinate effect riding on top of an expanding metric. The underlying rule about signals, world lines, and light cones is untouched. Feynman would tell you to keep your eye on that rule and not get distracted by how the coordinates are drawn. But there is one more extreme test of this speed limit sitting right at the edge of what we can observe, places where the escape velocity hits c itself and not even light can get out. If anything was going to push against the limit, it would be there, at the surface of a black hole, where the geometry becomes so warped that every path forward leads inward. How do you make a region of space where even light, moving at c, never gets out? Start with escape velocity. For any planet or star, there is a minimum speed you need to leave and never fall back. For Earth, that escape speed is about 11.2 kilometers per second, around 7 miles per second. For the Sun, it is hundreds of kilometers per second, a few hundred miles per second. If you throw a rock slower than escape velocity, gravity eventually pulls it back. Faster than that, and it can coast away to infinity. Now push that idea harder. Take a mass, squeeze it into a smaller and smaller ball, and watch what happens to the escape velocity at its surface. As the radius shrinks, the surface gravity increases, and the escape speed goes up. There is a critical radius where the escape speed hits c, about 300,000 kilometers per second, 186,000 miles per second. For a given mass, that radius has a name, the Schwarzschild radius. If you compress the Sun down to its Schwarzschild radius, it would be only a few kilometers across, a few miles smaller than many cities. If you did the same to Earth, the critical radius would be smaller than a marble, a couple of centimeters, less than an inch. Past that point, inside that radius, no signal moving at or below c can escape. That is the basic idea of a black hole. You could stop there and call it a dark object we can never see, but modern astronomy has gone further. It has actually imaged the environment around these things. The Event Horizon Telescope is not one telescope, but it is a network of radio dishes around the globe, linked together to act like a planet-sized dish. Using that setup, astronomers have resolved the region around the supermassive black hole in the galaxy M87, and the one at the centre of the Milky Way. In the images, you see a bright, lopsided ring of radio emission wrapped around a dark central patch, the shadow. The size and shape of that shadow match what general relativity predicts for light paths near a black hole. Photons that pass close by get bent and can orbit in unstable rings. Some fall in, some swing around and escape. The region where light can orbit or cross the horizon but never come back out shows up as the dark zone. The ring thickness, the asymmetry, and the diameter all line up with simulations that assume gravity is described by Einstein's equations and that nothing outruns c. So you have escape velocity hitting c, you have real images that fit the theory, but the most disturbing part is what happens to time near this gravitational edge. If you fall toward a black hole and carry a good clock on your wrist, you see it tick normally. 1 second is 1 second for you. You cross the event horizon, the boundary at the Schwarzschild radius, in a finite time according to your own clock, and you keep going inward. From your point of view, nothing magical happens at the horizon. The local physics is still the normal speed limit. Light still moves at c in your tiny neighbourhood. But someone far away, watching you through a telescope, sees a different story. As you get closer to the event horizon, your clock appears to run slower and slower. Signals you send out, light pulses, radio messages, get more and more stretched out in time as they climb away from the deep gravity well. Their frequency shifts down toward the red, then into radio, then effectively to zero. Right at the horizon, from the outside perspective, the time between pulses blows up. Your last signals are delayed without limit. In that precise sense, the event horizon is a one-way surface. For an outside observer, nothing at or below c ever quite makes it out once it gets too close. The information gets smeared over longer and longer times, fainter and fainter, until it is effectively gone. The geometry of space-time near the horizon tilts the light cones inward, so that all allowed future paths lead deeper into the hole, not out toward distant space. Even light, which has no rest mass and always moves at c locally, cannot reverse that tilt once it is inside. It is not that light slows down, it is that the direction of future for anything inside the horizon points inward. Trying to escape by going faster than c is not an option, because there is no faster than c slot in the rules. The space-time structure simply does not provide a path that climbs back out. For Feynman, this is the ultimate brutal demonstration of how absolute c is. You have an object made purely from the geometry of space-time defined by the point where escape velocity equals c. You have massless particles that always move at c along null paths, and still, once those paths cross the horizon inward, there is no combination of pushes, no engine, no extra boost that makes them come back. The rule is not try harder. The rule is all future directions from here lead down. This also kills a lot of casual sci-fi ideas in one stroke. You cannot imagine some rocket that accelerates at a crazy number of g and punches its way out of a black hole, because that would require world lines that tilt outside the allowed light cone. The light cone itself has tipped, and your future is trapped inside it. The no escape rule is geometric, not technological. Put all this together and you see the pattern. Escape velocity, shadows in real images, time dilation at the edge, light, cones tipping inward. All of it is built around the same number c and the same structure of space-time you have been following since the start. Black holes are not exceptions to the speed limit. They are places where the limit is used to its fullest, where the geometry forces even light to obey a one-way rule. But gravity does more than trap light. When massive objects move and collide, they also shake space-time itself, sending out ripples that cross the universe. If anything could have had a different speed of influence, it would be those gravitational waves. So the next question is sharp. Does gravity get its own private channel that outruns light? Or do those ripples also obey c right down to the last decimal place? How do you know gravity does not have its own private fast lane, a way to pull on things before light can even react? LIGO answers that by brute force. Each LIGO detector is an L-shaped vacuum tunnel with 2 arms, 4 kilometers long, about 2.5 miles. At the ends are mirrors. Lasers bounce up and down the arms, and interference between the beams tells you how long each arm is to incredible precision. When a gravitational wave passes, it does not push the mirrors like a wind, it stretches space in one direction and squeezes it in the other. The arm lengths change by less than the diameter of a proton, a distance of about a femtometer, 1/4,000,000th of a meter. Yet the instrument can pick that up. When LIGO first detected a gravitational wave, it saw a rising chirp signal. The frequency and amplitude increased to over a fraction of a second, then cut off. That pattern matched simulations of two black holes spiraling together and merging, simulations that had been run years before using Einstein's equations on supercomputers. Masses, spins, orbital decay, everything lined up. It was a direct hit. Spacetime really does behave like a medium that can carry waves, and those waves came from a violent event over 1 billion light-years away. So you have ripples in spacetime itself, crossing vast distances and moving mirrors on Earth. The next question is obvious. Do those ripples move at sea, or does gravity get to cheat? The cleanest test so far came from merging neutron stars. LIGO and another detector picked up a gravitational wave signal with a characteristic pattern that screamed two neutron stars in spiraling. Almost at the same time, gamma-ray telescopes saw a burst of high-energy light from the same patch of sky. Other telescopes then watched the optical and radio afterglow fade over days and weeks. Both signals, gravitational and electromagnetic, had travelled over 100 million light-years to reach us. The difference in arrival times between the gravitational wave and the first light was around a couple of seconds. Over such a huge distance, that means the speed of gravity and the speed of light match to within an insanely tight fraction. If gravity were even slightly faster or slower than light on cosmic scales, the gap would have been minutes, hours or more, not seconds. Instead, they move almost neck and neck. Within our current ability to measure, gravity and light propagate at the same speed. See, you can also cross-check this without waiting for dramatic mergers. If gravity acted instantly, or much faster than light, planetary orbits would look different. The way Earth orbits the Sun assumes that gravity responds to where the Sun is now, up to the finite light travel delay, not where it was long ago in some absolute sense. In a universe with instantaneous gravity, you would get subtle instabilities, like a tug always pointing to the current position instead of the retarded one. Precise tracking of planets and spacecraft does not show those instabilities. It fits a picture where gravity's influence propagates at sea. Binary pulsars are an even stricter test. A pulsar is a spinning neutron star that sweeps a radio beam across us so we see regular pulses, like a clock. In a tight binary, two neutron stars orbit each other and lose energy by emitting gravitational waves. As they radiate, the orbit shrinks and the orbital period changes. You can time the pulses to ridiculous precision and see how fast the system is losing energy. The data match the prediction from general relativity, which assumes gravitational waves travel at sea and carry away energy at that rate. If gravity propagated much faster or slower, the decay curve would not match. It does. All of this matters for the speed limit because it kills a common escape route. You might think, sure, light and electromagnetism are limited by c, but maybe gravity is different. Maybe it updates instantly and just looks relativistic on the surface. The observations say no. Gravitational effects, from orbital decay to neutron star mergers to cosmic structure, behave as if gravity is another field with disturbances that move at sea, not a separate channel that outruns light. When people try to quantize gravity and talk about gravitons, hypothetical particles that carry gravitational waves the way photons carry electromagnetic waves, the same logic from Feynman diagrams applies. You again have propagators, amplitudes for going from one space-time point to another. Those are built to respect the light's cone structure. Internal lines in the diagrams can explore all sorts of virtual paths in the math, but the measurable effects, like cross-sections or energy loss, are arranged so that they never let you send a controllable signal outside the C boundaries. The details for gravity are much harder than for quantum electrodynamics. The field equations are non-linear. The graviton couples to everything with energy and momentum. The math is nasty. but the key principle carries over. Disturbances propagate along paths limited by c, and the observable part of the theory is constructed to keep causality intact. There is no special exemption where gravitational information jumps ahead of light cones and fixes things in advance. So at this point, both major carriers of influence in the universe, electromagnetism and gravity, are locked to the same limit. Light pulses and gravitational wave arrive in sync over cosmic distances. Planetary orbits and binary pulsars evolve, as if nothing updates faster than c. Quantum field calculations for photons and hypothetical gravitons are written to respect the same causal cage. That sets the stage for one more big shift in how you think about things moving and signals being sent. Modern physics does not really talk about little pellets flying through empty space. It talks about fields filling all of space, and particles as excitations in those fields. In that language, information is not objects travelling, it is disturbances rippling through fields, and that rule that those ripples can never outrun c becomes even more important. So the next step is to strip away the last comfortable picture of particles as tiny bullets, and look directly at the field view, where c is not just a speed limit, it is the maximum rate at which any field configuration can change in a way that carries information from one point to another. How can you talk about speed limits if there are no real things moving, just fields everywhere? In modern physics, the basic objects are fields that fill all of space. There is an electron field, a photon field, a quark field, a gravitational field. These fields are present at every point, right where you are sitting right now. A particle is what you see when a field is excited in a localized way, a little lump of energy in that field. When you say an electron is here, what you really mean is the electron field has a localized excitation here with certain properties. Same for photons. They are not tiny light bullets, they are excitations of the electromagnetic field. That shift in viewpoint matters, because it changes what you even mean by signal or movement. Instead of thinking about hard pellets flying through empty nothing, you think about fields changing their configuration over time. The rules that control how those field changes spread are where c lives. The speed limit is not imposed on little balls, it is imposed on how fast field disturbances can propagate. Take a simple case turning on an electric charge. Say you suddenly create a charge at some point in space and you want to know how the electric field responds. One wrong way to think about it is to say, the field everywhere instantly rearranges. That would mean a point 10 light years away feels the new charge immediately, which would be a clear faster than light signal. What actually happens, according to Maxwell's equations, is different. The change in the electric and magnetic fields caused by that new charge propagates outward at c. If you are 1 light second away, about 300,000 kilometers, around 186,000 miles, nothing happens to the field where you are during the first second. After 1 second, the disturbance reaches you. If you are 1 light year away, you wait 1 year. In other words, the field learns about the new charge by a ripple that moves at c. There is no way to flip a charge on here and have the effect show up instantly there. The structure of the field equations enforces that finite signal speed. The same logic applies to switching antennas on and off, shaking charges back and forth or changing currents in circuits. The changes propagate outward at the speed of light in vacuum. This is where information gets a precise meaning. A message is not just some static pattern in the field. A static electric field that has not changed for 1 billion years carries no new information by itself. It is just part of the background structure. A message is a disturbance, a change in time. A radio station encodes sound as a time-varying electromagnetic wave. A radar pulse is a sharp transient. A gravitational wave is a time-varying curvature of space-time. In every one of these cases, the maximum speed at which those disturbances move is c. That is true in empty space. In materials, the effective speed of certain wave modes can be slower, because the field is interacting with matter, being absorbed and re-emitted, delayed and mixed. But even there, when you drill down to the underlying field description, there is still an upper bound on how quickly any real disturbance can move, and that bound is c. You can delay signals, you can shape them, you can slow them down with media, but you cannot make the front of a genuinely new disturbance jump ahead of the light cone. This is why when you talk about sending information, you're really talking about launching a controlled change in a field and waiting for that change to arrive somewhere else. A radio message from a spacecraft is a disturbance in the electromagnetic field that leaves the antenna, moves across millions of kilometers of space, and eventually hits a dish on Earth. A gravitational wave from a neutron star merger is a disturbance in the metric field, the space-time curvature that leaves the system and reaches detectors after travelling hundreds of millions of light years. In both cases, the maximum speed of that information transfer is locked to c. Feynman kept telling students, stop picturing little balls bouncing around and start thinking in terms of amplitudes, fields, and space-time diagrams. In the old pre-relativity picture, you could imagine tiny pellets shooting through space, carrying forces and signals, and just add their speeds like you add car speeds. In the field picture, that way of thinking fails. In space-time diagrams, you draw events as points and world lines as curves. Field disturbances follow paths that are tied to those light cones you have seen again and again. For light and other massless excitations, the world lines sit exactly on the edges of the cones. For particles with mass, the world lines stay inside. There is no line that legitimately tilts outside without wrecking the field equations and their consistency. So in that language, c is not the speed of photons, it is the maximum tilt any cause and effect connection can have in space-time. Tilt too far horizontally on the diagram, and you're asking for a link between events that are space-like separated, outside each other's light cones. The field description simply does not give you a way to create a real controllable disturbance that connects those events. Break that rule, and the whole framework collapses. You would lose energy conservation in relativistic collisions, you would lose unitarity in quantum field theory, you would lose the clean separation between cause and effect that the light cone structure gives you. You would open the door to the paradox loops you saw earlier, where signals go backward in time in some frames. The entire field picture is built on the assumption that c is the invariant cap on signal propagation. At this point, you have pushed the particle picture aside, you have watched muons and protons age slowly at high speed, you have seen black holes trap light by tilting light cones, you have watched gravitational and electromagnetic waves march across cosmic distance at effectively the same speed, and you have tied information itself to disturbances in fields that cannot outrun c. So the obvious next move, if you are still trying to cheat, is to stop thinking about moving stuff through space-time at all, and try to move space-time itself. If you cannot make a ship go faster than c through the grid, maybe you can bend the grid, ride a warp bubble, or cut a tunnel, a wormhole and jump through. That is where people push hardest against the limit, and where the equations seem to offer a tiny crack before slamming the door again. How do you cheat a speed limit if you're not allowed to move faster, but nobody said anything about moving the road? Here is the core of the Alcubierre idea. In the 1990s, Miguel Alcubierre found a solution to Einstein's equations where you do not push a ship through space at crazy speed. Instead, you take a chunk of space-time around the ship and move that chunk. In front of the bubble, space contracts. Behind the bubble, space expands. Relative to distant stars, the bubble can slide along faster than c, but inside the bubble, the ship just floats, locally at rest or moving at comfortable sublight speeds. From your point of view inside, you never break the local speed limit. Your clock and your physics feel normal. In the math, you define a warp bubble that scoops space from behind and dumps it in front. So the distance between you and your destination shrinks faster than light would cover the original gap. To an outside observer using standard cosmological coordinates, the center of the bubble can move superluminally. To you, it feels like sitting still in a small cabin while the scenery gets dragged toward you and past you at any speed you like. So if the equations allow that kind of space-time bubble, why aren't engineers drawing up warp drive blueprints right now? Because the same equations tell you what stress energy you need to create that geometry, and the bill is brutal. To generate the warp bubble, you need regions of space-time where the energy density is negative compared with empty vacuum. Not just low, Not just colder than cold, literally less than the energy of nothing. That is called exotic matter. Our current understanding of quantum field theory does allow tiny, brief regions with negative energy density. The classic example is the Casimir effect, where two conducting plates close together experience a small attractive force because of how vacuum fluctuations are altered between them. That can be described in terms of a slight negative energy density in the gap. But those effects are microscopic and short-lived. They live at scales of nanometers and microseconds, not kilometers and years. Warp metrics like Alcubierre's need something completely different. Macroscopic amounts of stable negative energy, smeared over distances on the order of the bubble size. Early estimates of the required energy were ridiculous, involving the mass energy of planets or stars, even galaxies, just to move a modestly sized ship. Later work has played with clever shapes and dynamic bubbles to reduce the requirement, but it is still far beyond anything remotely practical. And on top of that, we do not even know if the necessary negative energy configurations are allowed once you include all the consistency conditions from quantum field theory, not just classical general relativity. So right now, the warp bubble geometry sits in a strange zone, mathematically allowed as a solution, physically unsupported because the material you need to make it is not known to exist in usable form. You get yes on paper and no in reality at the same time. If bending space in front and behind the ship looks shaky, what about cutting a tunnel through space-time instead of going around? Can you just punch a hole and take a shortcut? That is the wormhole story. General relativity admits solutions that look like tunnels linking two distant regions of space-time or even two different universes. You can draw diagrams where a traveller enters the throat of a wormhole near Earth and exits near a distant star, skipping the long slog through normal space. From the outside, the path looks faster than light. From the traveller's point of view, they never exceeded c locally. The catch again is support. To keep a wormhole throat open so something macroscopic can pass through, the equations say you need exotic matter with negative energy density. Ordinary matter with positive energy density makes gravity pull inward and tend to close the throat. Negative energy would push outward, fighting that collapse and holding the tunnel open. Without it, the wormhole pinches off before you can use it. Even if you grant yourself exotic matter, there is a nastier problem. If you drag one mouth of a wormhole around in space-time, you can arrange things so that entering one mouth and exiting the other lets you effectively travel into your own past. That is a time machine. When people simulate these setups and include quantum effects, they often find that vacuum fluctuations near the would-be time machine blow up, the energy density diverges, and the wormhole collapses under the stress. It is as if the laws of physics tolerate maybe you can connect two distant points on paper, but as soon as you try to use the construction to create paradoxes, quantum back reaction slams it shut. So both big hacks, warp bubbles and traversable wormholes, lean on a resource we have never seen in macroscopic, controllable form, large negative energy. And when you try to push them hard enough to break causality, the same theories that allowed them appear to fight back and destabilize them. This is exactly the kind of situation where you can hear what Feynman would say. First, the math is interesting, but show me something I can build, measure, or collide. Second, as long as every real experiment from particle physics to astrophysics follows the same rule that you cannot locally send information faster than c, speculative metrics stay in the fun to think about drawer. Right now, that is where warp drives and usable wormholes live. We do not have the exotic matter they demand. We do not have observations of stable negative energy structures in space. We do have a huge set of precision tests that all point to the same speed limit, from GPS to binary pulsars to gravitational waves and cosmic rays. The universe keeps enforcing the same rule in every domain we can probe. So after all these attempted cheats, what are you left with? You have a constant c that shows up in electromagnetism, in relativity, in quantum field theory, in gravity, in cosmology. You have field equations and spacetime diagrams that fall apart if you try to let anything outrun that constant. And you have real hard data that always lands on the same side of the line. The remaining question is not, can we hack the limit? It is, why does the universe need this limit at all, and what breaks if you take it away? If you step back and look at everything you have seen, particles aging slowly, black holes trapping light, galaxies receding, quantum amplitudes cancelling outside light cones, you start to see C not as a restriction, but as the number that holds the whole structure together. Why does the universe care so much about one number, and why does it punish you every time you try to ignore it? By now you have seen C from every angle. As a plane speed, it is about 300,000 kilometers per second, roughly 186,000 miles per second. That is the raw number. But deeper than that, C acts as a conversion factor. Multiply time by C and you get a distance. Multiply mass by C squared and you get energy. Use C and you set the slope of light cones in spacetime, the boundary between can affect and can never affect. So when you say speed of light, you're really talking about the constant that translates between almost every major concept in modern physics. Time into space, mass into energy, local behavior into global geometry, cause into effect, change C, and you're not tweaking one piece of the system, you are changing the translation rule that connects all the pieces. That raises a sharp question. What kind of universe would you get if this number were even slightly different? Or if there were no upper limit at all? Start by lowering C. Suppose light and all massless fields move much slower. Now C squared, the conversion between mass and energy, shrinks. That changes how much energy you get from nuclear reactions, both in stars and in reactors. Fusion in stars depends on a delicate balance between gravity trying to crush the star and pressure from nuclear burning pushing out. Change C, and you change the rate at which mass turns into energy. Some stars might never ignite, others might burn violently fast and blow themselves apart. The window where long-lived stable stars like the Sun exist could narrow or vanish. Drop C enough, and the speed limit hits everyday scales. Relativistic effects start to kick in at lower and lower velocities. Chemistry which relies on how electrons move around nuclei would shift. Atomic energy levels depend on C through the structure of quantum electrodynamics. Molecules might not form the same way. The periodic table would not look like the one you know. The chance of getting complex, long-lived structures like DNA or proteins could fall off a cliff. Now raise C to some enormous value. At first that sounds great. Higher speed limit, more room to move, but C squared blows up even faster. A small mass now corresponds to a ridiculous amount of energy. Nuclear processes become extremely energetic. Particles confined in atoms could behave differently, because relativistic corrections become important in new regimes. The balance between electromagnetic forces and quantum effects shifts. The stable, quiet, low-energy chemistry that life depends on could be drowned in much more violent interactions. Then take away the limit altogether. Let signals propagate arbitrarily fast. You instantly kill the clean light cone structure that has been guiding you this whole time. Without that structure, there is no universal way to say which events can influence which. You can set up paths where signals go around loops in space-time and arrive before they were sent, at least in some frames. Causality breaks. Energy conditions that currently keep processes finite can fail, opening the door to runaway phenomena where infinite energy can be extracted from fields or from the vacuum. The mathematical frameworks we use now, both classical and quantum, would not just need a patch, they would crumble. So the cosmic speed limit is not a random rule meant to annoy future starship captains. It is a condition for having a universe that is stable, causal, and structured enough to build atoms, stars, planets, and you. A universe without a limit, or with a wildly different one, is not just a faster or slower version of this one. It is a fundamentally different game, and in most simple variations, the game does not last long or does not produce anything interesting. At this point, you are standing in front of a choice. You can keep fighting the weirdness and say, this feels wrong, or you can do what Feynman did and say, this feels wrong, but the universe clearly does not care, so I will learn to live with it. That was his real talent. He did not try to make the world intuitive. He tried to make the weirdness usable. Muons that should die in the upper atmosphere but hit the ground anyway. Protons in accelerators that refuse to reach C no matter how much energy you pump in. Clocks on satellites that tick at different rates than clocks on Earth. QED predictions lining up with experiments to insane precision. Gravitational waves and gamma rays showing up almost together after flying for 100 million years. All of these are separate experiments, with different instruments, different teams, different systematics. They all point to the same pattern. There is an invariant speed. It links space and time. It sets the energy cost of mass. It controls how fields propagate, how black holes trap light, how the universe expands, and how information moves. That speed is c. Once you accept that, the universe stops looking like it is breaking your expectations and starts looking like a machine that was always built around this number. Time dilation, length contraction, redshifts, horizons, light cones, path integrals, all become different gears driven by the same rotation rate. You stop asking, why won't nature let me go faster, and start asking, what else becomes possible once I take this limit seriously? Where does that leave you, stuck with technology that will probably never get you close to C, let alone past it? You will almost certainly never fly at twice the speed of light. You will probably never ride a 0.99c starship and come back decades ahead of everyone you knew. But the same constant that blocks that fantasy is already working for you all the time. Your GPS depends on relativity built around C to keep your location from drifting by kilometers every day. Electronics and fiber optic networks move information near the practical limit set by light in materials. Nuclear physics, which underpins everything from stars to potential future reactors, is governed by the mass-energy conversion that uses c² as its exchange rate. Our models of galaxies, black holes, cosmic evolution, and the early universe all use C as a core parameter. Without that, you would not have a consistent picture of where you came from or what you are looking at in the night sky. So the same rule that says no faster than this is also the rule that gives you accurate maps, working electronics, stable stars, and a coherent story of the cosmos. It is a limit, but it's also a key. What Feynman uncovered, and what you have just walked through, is that once you stop treating C as just a big speed and start using it as the fundamental unit that connects time, space, mass, energy, and information, the whole structure of physics tightens up. The universe becomes stranger than your intuition, but it also becomes more intelligible. The speed of light is not just how fast light goes, it is how reality updates everywhere for everything. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.